Any questions?
Yeah, I was looking at the master set that's due Monday, the 20th.
Okay.
And there's two questions, that have, it says 4 wires are running parallel on the corners of a square. The wires are parallel to the x-axis and hit the YZ plane at a few points. The first 3 have current running through the positive x direction, and the last one runs the negative x direction. What is the direction of the total magnetic field at the point something? Can you just do an example of those?
Good. It's just asking for direction.
Yes, it's not numbers. And by parallel to a corner of a square, can you kind of show what that is?
All right. So let me see the problem before I start shooting off on some bizarre tangent.
Number 13.
Four wires running parallel at the corners of a square.
My imagination was like 2 up here and 2 down here.
They're going parallel to the x-axis and hit the YZ plane. Okay. And then, let's see, X. So X is coming out at us.
Okay.
Do the attempt like that. So X is perpendicular to Y and Z, which pretty much is all of your experiences with axes, I'm sure. It is, so it hits the YZ plane. So if I had a square right here, it's hitting the YZ plane, so the wires are running out like that. So we've got 4 wires running parallel. And so I'm asking for the magnetic field at some point. And I don't remember what that one is, but we'll just say that at this point right there, the current's going in. Just trying to be consistent with my notation, so x-axis is coming out. Here, why don't we say the current's going out. Here we'll make it out, and there we'll make it in. Each one produces a magnetic field, because as we've talked about, and it seems to be reality, and you noticed in the lab the other day, potentially. Current creates a magnetic field. So, using the right-hand rule, my current's coming out here, so the magnetic field from this wire right here is going around like this. Magnetic field from this one also going counterclockwise. From here, going clockwise. And from here, clockwise. So if I wanted to find the total magnetic field, I've got 4 vectors that I'm adding together. If I'm in the middle, from this one, the magnetic field is going that way. From this one, it's going that way. From this one, it is going that way. And from this one, it is going, let's see, oh, wait, the last one was off. From this one right here, it's going this way. From this one, it's going that way. So the net magnetic field would be in that direction.
Why are the top 2, I know one is negative, so it's going to have the opposite of the other 3. Did you just make 2 negatives and 2 positives?
I had 2 going into the board and 2 coming out of the board, as an example.
So you just have the magnetic fields and you kind of just see which way they point and then make a vector in between?
Yep. That's pretty much it.
And then one of the other questions I had was, there was another problem coming out, is you had a magnetic field, I assume just like a box or something, and then you drop a piece of tin foil like through it, and how would it affect it? I just didn't know for sure about it.
So you're just dropping a piece of metal through a magnetic field?
Yeah, and seeing what direction it would go.
Is it a loop of wire, or is it a solid piece?
I think it's solid.
Is
just says a piece of aluminum is dropped vertically downward between the poles of an electromagnet. They don't say.
Between the,
Does the magnetic field affect the velocity of the aluminum? If yes, how?
alright, so the poles of, so I'm picturing a north and south, so a piece of aluminum is dropped in between.
Yes.
Is that, so I have a piece of metal that is going through it. So if you think about, it's chapter 22. What I'm thinking of is a chapter 23 question. Let me see if I actually have a copy of the master set here. I assume that was from the master set?
Yeah, it's the first one, I believe. My idea before like starting the question was it would just slow down, but eventually it would go through it, because based off the stuff we have, we don't have like if it would completely push it backwards.
Yeah, the only way they could possibly push it backwards would be superconducting, but it's aluminum or some sort of metal foil. Let's see, so as it falls, I got positive and negative charges in there.
Am I on the right track with that? Like it'll slow it down?
Let me see the wording again for that one.
It's the first one? Yeah.
All right, piece of aluminum is dropped vertically downward between the poles of an electromagnet. Note that magnets do not stick to aluminum without an adhesive. I need to adjust that. Does the magnetic field affect the velocity of the aluminum? If yes, then how? If no, why not? So I have two answers running through my head. All right. If I get a north and south pole like that, well, first off, it's not going to make it go faster. So it's either going to slow it down or have no effect. We have a motional EMF that's being induced. So I have a magnetic field that is flowing, let's see, north-south, so externally, the magnetic field goes this way. I have positive charges going down. There we go. I have positive charges going down. Magnetic field's going into the board, so the positive charges would be forced that way, the negative charges would be forced this way. Well, the positive charges aren't going to move, except downwards. But I would get a buildup of negative charges over here. So I would have a current flow in that direction within this piece of aluminum. That would create a secondary magnetic field that is going around like this. In like that. Which is perpendicular to the other magnetic field. Trouble is I'm using chapter 23 stuff for this explanation. So I'm trying to remember what the chapter 22 version is.
But to start it, the magnetic field induces a current on the cube, I'm just gonna call it cube aluminum, which then makes a current in the cube, and then the current makes its own electric field, and they interact with the.
Yeah, but they're interacting perpendicular to each other, so it's not like you're gonna have a weakening of the magnetic field.
So it's different interactions? What,
Yeah, see, before when you cause like the wires to move out or move in, the induced magnetic field counters the other magnetic field, and so there's a weakening. Here, off a magnetic field that way, and then another magnetic field, I guess, on top that way. So they will not reduce each other, they'll create a magnetic field with a higher magnitude in that direction.
So, in this situation, you have these two things and they kind of combine just to go diagonally?
Yeah, it's constructive interference.
Okay. So, would it move down or would it move like outward, or no, I guess it'd be,
It would just fall. Through the electromagnet.
because in my brain, it
Missing.
wouldn't make sense for it just to shoot off in the combined vector.
No, I mean, that's just the direction of the total magnetic field.
Yeah.
All right, so if we did it in terms of force, the force would be exerted left or right. I'm gonna go grab something, I hope, if I can find it. All right, it's going down.
Mm-hmm.
Magnetic field is going that way, not that way. So the force on the particles would be this way. The force on the positive charges would be into the board, so that's the direction of a current within this piece of aluminum foil. So the current is going into the board. That current into the board means that it's creating a secondary magnetic field going like this. And so my magnetic field is bolstered on the bottom and weakened at the top. So therefore there would be a net force upwards.
So go up.
Sorry, not a net force, a secondary force acting on this. There's force of gravity, then there's a secondary force acting up, which would slow it down.
Now, I know you just put the south and north poles on those sides. Could you just flip it and be the other direction and still fall down?
If I flip north and south, then the current induced would
There,
be
just
the other direction, and magnetic field would go the other direction, and the secondary magnetic field would go the other direction, and it would still slow it down.
So, the first magnetic field causes a current in the box of aluminum, which gives it another magnetic field, which weakens the original one, and so it just slows down, but still falls.
Yeah, weakens on top and increases on the bottom.
Thank you.
Okay. That's probably more of a chapter 23 question. What the heck?
The more you know.
Dun, 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 dun. Other questions? All right. We last left off. We had just done the
It was,
motional EMF.
It was Princess Bride reference.
Yeah, motional EMF. Princess Bride reference. All right, so we've talked about the fact that charges, moving charges create, well, in essence, that's a current, which means that there's a magnetic field, and just for the sake of ease,